Alrighty, good afternoon, lads and ladies. Sorry for the late start here. I got a few folks doing heavy duty things in office hours, and I had to make sure they were doing good, but everything is all sorted out now. So you and I can continue on our little adventure here into the land of integral calculus, sorting out these problems related to areas and in the physics context, distance. I think it would be nice if we began just with one or two kind of standard problems here. Let me just grab some from here. We have the opportunity to calculate Okay. Yeah. Well, 1 plus x squared, that's so close to one we've done before. This is basically one out of your homework problems. Sin x is one of those. 2 plus sin x, upper and lower sums now. Yeah. All right. So let's do this one. I'll put the title card in here first. This is MAC 2311, section 004, which is a Calc 1 class, and the date today is the 25th of March, 2022. Today I want to do a couple of things, a little more practice. With Riemann sums. I want to do at least one where we're estimating an area with a finite number of sums. That'll be our last practice problem like that. And at least one where we're calculating an exact area using a limit of a Riemann sum, because they have slightly different fields, although they are sort of technically the same thing. They do have a slightly different feel, and of course finding the exact area is more work. So we're going to do that. And then the other thing I want to do is introduce the notation and concepts that we're going to be working with next week. So next week, we're going to learn about the fundamental theorem of calculus. And I just want to kind of get you ready for the notation and ideas there. I'm not going to drop the theorem itself on you, but this way you'll have some familiarity with the symbols when we actually go in and do the math on Monday. So more practice with Riemann sums and a little intro to integral notation. Let's do it. So this is straight up one of your homework problems. I'll kind of modify just a tiny bit so it's not boring. Let's find, let me say it like this. Let's approximate the area under f of x equals 1 over x squared from x equals 1 to x equals 5 using 4 rectangles with both right and left. And points. So the graph of 1 over x squared is one that we should know. It is nice on all of these to begin with a picture. I'm going to exaggerate the scale a little bit because 1 over x squared goes to 0 very quickly. So I'm going to kind of stretch this out a little. And you know, he blows up to infinity as we go towards 0. Of course, this is an even function, so the graph is symmetric on that side. But I don't particularly care about all that because I'm looking here from 1 to 5. So the area we're trying to approximate is this pencil shaded area. And we're told to use 4 rectangles. We're going to do both right and left endpoints. So we'll have to draw this picture twice. If I come in here chopping this thing up, 2, 3, 4. And we want to use 4 rectangles. So I've got 1, 2, 3, 4 here, right? I guess if we're being very careful about it, the first thing we would do is calculate delta x. Delta x is always b minus a over n. Remember, n is the number of rectangles. A and b are the x values of the interval over which we're finding the area. So this would be 5 minus 1 over 4, which of course is 1. And the xi's then, these are always a plus I times delta x. So x0 is 1, x1 is 2, x2 is 3, x4 is 4, and x5 is 5. Oh, let me use a different color for the rectangles. So I'll draw this with the right endpoints first. If we're doing right endpoints, then my rectangles will look like this. And I think it's pretty clear that this is going to be an underestimate. And we discussed that for a decreasing function, Rn will always underestimate and Ln will always overestimate. So that's no surprise.
Professor, I think you skipped x3 equals 4, but you put x4 equals 4.
Oh,
if that makes sense.
Yeah. Sorry. Yeah, x3 equals 4 and x4 equals 5. Sorry about that. Yeah, very good. 0 through 4, we should have a total of 5 of these things. That's good. I'm sorry. So the picture we've drawn here is for R5, and we know that R5 is the sum from I equals 1 to 5, f of xi times delta x, which is f of x1 times delta x plus f of x2 times delta x plus f of x3 times delta x, x4 times delta x plus f of x5 times delta x. So delta x is 1, x1 is 2, so this is f of 2 plus x2 is 3, so this is just f of 3. It's f of 4, it's f of 5. All right, each of those delta x's is just 1. And then f of 2 is 1 over 2 squared. F of 3 is 1 over 3 squared. F of 4 is 1 over 4 squared, and f of 5 is 1 over 5 squared. So we get 1/4 plus 1/9 plus 1/16 plus 1/25. And this is one of those places where I would say there is zero shame in using a calculator. Let we get 0.46, blah, 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 blah. 46361, which has a ratio is 1669 over 3600. Any questions on the calculation of R5 or what any of these symbols mean or notation now that we've had some time to chew on it and review everything?
On like tests and on our scratch work, do you want both the decimal and the exact?
No, I'm not picky. Whichever version you feel more comfortable with is fine with me.
Okay, thank you.
Oh, I just realized I wrote R5. Yeah, we're calculating R4. I'm so sorry. 4 rectangles. We don't have this fifth term. I had to stare at that for a minute going, don't I have an extra term here? No, no. Okay. So let's try the same thing again, but using L. This time we're going to calculate L4. I'll redraw the picture. I know WebAssign gives you the option to kind of just click the right picture. I really want to encourage you to draw the picture yourself because there will be test questions where I ask you to sketch a graph and sketch the approximating rectangles and all that stuff. So definitely do yourself the favor of practicing these. It's a nice opportunity to review the graphs of parent functions and basic functions that we should know. If I come in here, making my rectangles with left end points, those will look like this. So the height coming from over here. Height coming from over here. Height coming from here. And the height coming from here. And this one we can see is going to be an overestimate. There's lots of blue stuff that is outside the pencil shaded area. Delta x is still 1, and the xi's are still the same as they were before. So L4, remember for the left endpoints, you sum from 0 up to n minus 1. So rather than summing from 1 to 4, this will be the sum from 0 to 3. F of xi times delta x should be f of x0 times delta x plus f of x1 times delta x plus f of x2 times delta x, f of x3 times delta x. X0 is 1, so this is f of 1, and delta x was 1. F1 is 2, so this is f of 2, and continuing f of 3 and f of 4, right? Each of these heights is f of 1, f of 2, f of 3, and f of 4. So that, because f of x is 1 over x squared, this is 1 over 1 squared, 1 over 2 squared, 1 over 3 squared, and 1 over 4 squared. So if we add a 1, and erase the 125th, there we go. as a decimal, that's 1.42361. It's a fraction. 205 over 144. This is not a function where I can find the exact area doing a calculation like we did for x squared. At least not easily, right? If you try to set up this sum in terms of n, right, leaving n as a variable, we don't have a nice summation formula for 1 over I squared. Now there are ways to do it. You can have a common denominator and then use one of the other summation formulae, but it's generally quite nasty. So for a problem like this, a function like this sort of approximation is the best we can do until we develop the deeper skill here, the integral. Warming up, getting closer to that. Let me go ahead and show you the notation and then work a problem or two finding exact areas. So any questions about either of these calculations? Or either of the pictures? Okay. So here's the notation. I'm going to continue to assume that f is a continuous function and that f is positive. And then next week, we'll see how to adapt this if either of those conditions break. But if f is a positive and continuous function on the interval a to b, then the exact area bounded by f of x and the x-axis is called the definite integral of f from x equals a to x equals b, denoted. This is like a big curly long S, right? Like the letter S from our alphabet. And you put a little a down here and a little b up here. So this is read as the integral from a to b. And then inside here, we write an f of x times dx. And we've seen in the Leibniz notation for derivatives before that dx is like the denominator in dy dx. It represents an infinitesimally small change in x. So you can think of dx here as like an infinitely small width. And you can think of f of x as the height. And remember where this comes from. We think of this as the limit as n goes to infinity of the right endpoint Riemann sum. Lim n to infinity, sum I from 1 to n f of xi times delta x. So it's kind of like in the limit here, as n goes to infinity, you know, delta x is b minus a over n. So the b and the a, those are fixed constants, but n is getting bigger and bigger and bigger. So delta x is getting smaller and smaller and smaller, right? As you have more and more rectangles, each one of them is narrower and narrower. So this delta x kind of turns into this dx in the limit. The f of xi, remember the xi's are like the sample points on the interval a to b. Well, instead of just having a finite number of those as n goes to infinity, remember there's n plus 1 sample points or n subintervals. So as n goes to infinity, you no longer have just a few x's that we call xi. You're actually talking about every x value between a and b. So here x represents the continuous variable running from x equals a up to x equals b. So this width becomes this infinitely small width. This finite number of heights becomes this infinite number of heights. And the symbol we use for a continuous summation is the curly s, kind of like the continuous version of this capital sigma, which is the discrete summation or finite sum. So this is the definition of the definite integral, and this definition will stay the same even when we extend to functions that are not continuous or functions that are not positive. But for right now, for today at least, I want you to think of the function as being positive, so we don't have to worry about signed areas. So let me craft a fun function here. Let's find this area. Let's find the area underneath this guy. Right here. And let's find it exactly. I'm going to phrase this in the way that the homework problems you'll be seeing next week are phrased. So I'm going to say evaluate the integral from 0 up to 1 of x minus x cubed dx using the definition. I think I only gave you one homework problem like this, and it wasn't written this way. It was said, you know, just find the exact area bounded by such and such curve. It's going to run similar to how we found the 1/3 as the exact area under x squared from 0 to 1. But the sum is going to be a little bit more complicated. We'll have to use some of those special summation formulas and some of the rules. I can toss in a quick sketch here. This guy has roots at 1, 0, and -1. So it's going to be something like this. I'm just looking at it. I'm not going to bother drawing in any rectangles here because we're sending the number of rectangles to infinity, and it's hard to draw an arbitrary number of rectangles. My hand gets quite sore after a few of them. So we just have to remember the definition, which is this thing. That, of course, requires calculating delta x and xi. So delta x is b minus a over n. We're integrating from 0 to 1. So a is 0, b is 1. So this is 1 minus 0 over n, or just 1 over n, similar to before. And the xi's, those are always a plus I times delta x. A is 0. This is 0 plus I times 1 over n. You could write that as just I over n if you wanted to. So then the integral from 0 to 1 of x minus x cubed dx should be the limit as n goes to infinity of sigma I from 1 to n. F of x here is x minus x cubed. So this would be xi minus xi cubed times delta x. And I'm just going to plug in those pieces. Is everybody comfortable with why I'm writing this? This is your f of xi. This is your delta x. And you see the analogy, right? Just like shape-wise, this thing kind of looks similar to this thing. Good mathematical notation should always be evocative of what's going on. Now the xi's are I over n. So this is I over n minus I over n cubed. And delta x is 1 over n. When we did the x squared from 0 to 1, we found that 1/3. There's only like one term in there that we had to deal with. But here there's multiple terms separated by subtraction. And in order to deal with a sum like that, we're going to want to distribute this 1 over n. Well, yeah, we want to split it up. That's the game. And in order to split it up, I think it is easiest if we distribute and rewrite as follows. This I over n times 1 over n, that's going to be I times 1 over n squared. This is I cubed over n cubed, so it's going to become I cubed times 1 over n cubed times 1 over n is 1 over n to the 4. And now I can use the linearity of the sum to split this into two sums. So I'll write limit and then a big open whatever parentheses bracket you want to use. Sum I from 1 to n, I times 1 over n squared, minus sum I from 1 to n. I'm splitting up the sum, I cubed times 1 over n to the 4. So I'll just take this single sum with the subtraction inside, and I split it up into two sums with the subtraction outside. Because I know how to handle the sum from 1 to n of I, and I know how to handle the sum from 1 to n of I cubed. We have summation formula for each of those. Handling them separately, I can invoke my summation formula. If you're being very careful about your notation, you might bring the 1 over n stuff out. So this is 1 over n squared, sigma I from 1 to n of I, minus 1 over n to the 4, sigma I from 1 to n of I cubed. Now, according to baby Gauss, the sum from 1 to n of I should be n times n plus 1 over 2. And the sum of the first n cubes is the square of that. That was that cube result. So each one of those simple sums now I can replace using the summation formula. And it becomes a matter of taking the limit. So I can distribute upstairs here. I get n squared plus n, and multiply downstairs here, 2n squared minus, this will be n squared times n plus 1 squared over 2n to the 4. The first piece is pretty much ready to go. We can take our limit here if we remember enough how to take those limits. Here I need to FOIL this out and do a little bit more work. So I'll go ahead and leave that first piece alone in this step. N plus 1 squared is n squared plus 2n plus 1. So when I distribute the n squared, that's going to be n to the 4 plus 2n squared, plus, 2n cubed plus n squared over 2n to the 4 like this. What is the limit of the first piece? Oh, did I miss something here? Oh, sorry, this 2 squares to a 4. Yeah, this should be a 4. Okay. Yeah, definitely fix that. N times n plus 1 all over 2, all squared is n squared times n plus 1 squared over 2 squared, which is 4.
I have a quick question.
Yeah.
The other day when we were going over the I cubed part, I wrote the square root of n times n plus 1 all over 2, but it's actually
Should be
n
the square.
plus.
Yeah.
Okay. I just wanted to make sure that I got that right in my notes.
No, I understand. Yeah, definitely the square of rather than the square root. Okay. So we're happy and comfy up to here. How do I take the limit as n goes to infinity of? Let's just talk about this first piece. Remember when we did limits at infinity? Did this a few different ways. You guys remember this trick? You divide top and bottom by the fastest growing term. We can use that in both of these. The trick we called renormalization. And it's equivalent to splitting up each fraction because each fraction just has a single term downstairs. If I divide the top and bottom by n squared here, I'll get 1 plus 1 over n divided by 2 minus, if I divide top and bottom by n to the 4 here, I'll get 1 plus 2 over n plus 1 over n squared divided by 4. Let's do that. Renormalization trick. So as n goes to infinity now, 1 over n goes to 0, 2 over n goes to 0, 1 over n squared goes to 0. So this becomes 1/2 minus 1/4, or just 1/2. So that is the exact area bounded by the function f of x equals x minus x cubed from 0 to 1. Questions on this calculation?
What happened to the like the n4 n to the power 4 plus 2n to the cube plus n squared? On the next line you wrote 1 plus 2 over n plus 1 over n squared. I'm confused how you got there.
So what I'm doing here is dividing this guy. I divide top and bottom by n squared. So I can think of this as 1 over n squared, and this times 1 over n squared. Here I divided top and bottom by n to the 4. So in each of those expressions, I divide top and bottom by the fastest growing term. N to the 4 divided by n to the 4 is 1. 2n cubed divided by n to the 4 is 2 over n. And n squared over n to the 4 is 1 over n squared.
Okay, I see. Thank you.
Yeah, no problem. So good questions. Other questions? What else is on your mind?
Wouldn't the answer be 1/4?
Oh, did I write? Yeah, yes, it would. Sorry, my brain is in a weird place today, I guess. 1/2 minus 1/4 is definitely not 1/2. It is 1/4. Yeah. Thank you. Yeah, Eric caught that too. Thank you, Eric. Other questions on the calculation here? Okay. I don't want to reach too far into next week's material. I'm hesitant to dig into 5.2. So let's see if we can find another 5.1 problem here that feels like it's worth our time. We just did something like that. We can take a look at something like 23 or 25. Those are fun. So, say find an expression for, and this I'll write as an integral from 0 to pi of the square root of sine x. X has a limit. Do not evaluate. So here I'm going to phrase this using our new notation. Instead of saying find the area under this function from 0 to pi, I'll just say find an expression for the definite integral from 0 to pi of square root of sine x dx. And we do not need to evaluate. So kind of the idea here is you just have to put the pieces together. We see from the integral that a is 0 and b is pi. The function f of x is the square root of the sine of x. So I can calculate my delta x as b minus a over n, which is going to be pi over n. The xi's are always a plus I delta x. A is again 0. Delta x is pi over n, so this is I times pi over n. And that means that by definition, this integral, which is measuring an area, would be the limit as n goes to infinity of that right endpoint Riemann sum with n rectangles, which is the same limit we were just working with. Sum I from 1 to n, f of xi times delta x. And we've calculated all the things. The xi's are I times pi over n. And delta x is just pi over n. And finally, we know what the function f is. It's the square root of the sine of whatever is inside here. So square root of sine of I pi over n. Oops. And that would be our final answer. The other problem I mentioned is the same thing, just going the other way. Somebody gives you an expression like this, and you have to reverse engineer the function and the a and the b. And it's not terribly hard, but it's something you want to be familiar with. Any questions on how we came up with this guy? Then let's try number 25. Said determine a region whose area is equal to the limit. And I will find tangent f, I will find. So find n times the tangent of n. So we just went in the kind of forward direction where you know the function, you know the region, and you want to write it as a limit. Now we want to go in the backwards direction where you're given the limit and you want to describe it as an integral, right? As an area of a region bounded by a function. The delta x piece from the last problem was pi over n. And here we have something looking kind of similar, only it's pi over 4n. The function f of xi from the last problem came out to this thing. And here we have something looking like this. So this is playing the role of delta x, and this is playing the role of f of xi. So f here is the function tangent x. And the xi is I times pi over 4n. Also, we recognize that the delta x piece here is the pi over 4n. And comparing these two, we can deduce that a must be 0. Right? Because we know that xi is always a plus I delta x. And this piece is just I times this piece. So this is b minus a over n for some choice of a and b. We can tell that a is 0 because this xi is just I times delta x, no something plus I times delta x. So this is just b over n. That's a equals 0. And that tells you that b is pi over 4. In other words, this limit is measuring the area under the tangent function from x equals 0 to x equals pi over 4. And if I want to, I could write that in our fancy new notation as the integral from 0 to pi over 4 of tangent x dx. Okay. There is just one other thing I want to show you today. And it's not something you're going to need for your homework this week, right? The homework this week is quite short and it's all just the stuff that we've been doing. The one other thing I want to show you today is meant to kind of get your brain ready for what we're going to do on Monday, similar to introducing this notation. Before I switch into that mode, is there any question you guys would like to ask regarding section 5.1 or any of these examples?
Can I have a real quick, it's so basic, but
Oh.
I'm having trouble grasping it, like where you get the xi's, like when you're adding it all up and you say it must be 0. Does that
So
make
you're
sense?
asking, like in this context, how I was able to get that a is 0?
Yeah.
So I know that, I can annotate here in red. I know that xi should be a plus I times delta x. And I know that delta x is this pi over 4n. So if I'm going to have, if we want to kind of set up an equation we could solve, I could say that a plus I delta x is in this case equal to, I say it like this, is equal to xi. I know what delta x is. It's 4 pi over 4n. And I know that the xi are just the things inside the function. So that's pi over 4n. So just kind of plugging in here all the things I know. I don't know a, but I want to solve for a. I think it's one of those things that's almost easier to see than to solve. But if I put the I pi here, multiplying the I times pi over 4n, and then subtracting that quantity from both sides, we get a is 0. So what I see is that inside here, it's not like something plus I pi over 4n, it's just I pi over 4n, which means the something that should come before the plus must have been 0.
Okay, thank you.
Yeah, no problem. It never hurts to be extra careful here. And it's worth mentioning that a problem like this actually has more than one right answer. Let me try and explain that. So we were able to deduce that that limit must represent this area, right? So here's the tangent function, there's the area bounded by tangent, and the x-axis from 0 to pi over 4. Oh, that's going to get cluttery, isn't it? How about here? So what if I shift the whole function to the left, to the right by pi over 4? Well, then I could say that. Notice the red and only set these to match colors, right? The red and black areas are the same. So you could say that this is the area under tangent from 0 to pi over 4, and you'd be correct. Or you could say that it's the area under tangent of x minus pi over 4 from pi over 4 to pi over 2. I could shift this by some other amount, right? There's infinitely many correct answers here. It's just that this is sort of the easiest one to come up with. And oftentimes when you look at these problems, I think they've gotten better about this. There used to be some ambiguity. That was here, right? Oh yeah, no, so this is an older version of the book. It still has the ambiguity. If you look at your actual homework problems, they'll say where A is this, right? They'll tell you the left endpoint of the interval because they don't want you to be concerned about the possibility of these shifted answers coming in and changing things. But either one of those would be a reasonable answer. And I think the nicest way to come at these is to try and think of these as being as simple as possible. So think of this as I times delta x, think of this as delta x, and then you can solve for your A if you need to. Okay. Our big goal next week is going to be to connect the stuff we've been doing lately, finding areas and whatnot, with the calculus operations that we learned earlier in the term, namely the derivative. In order to do that, I want to define something for you. We say that capital F of x is an antiderivative for little f of x on the interval I. And generally, we don't really care about the interval, but we're being careful on the interval I, if capital F primed of x is equal to little f of x for all x's in that interval. Focus. So for example, an antiderivative for little f of x equals x cubed would be, there's more than one of them. I just have to think of some function that when I differentiate it, I get x cubed. How about this guy? Because if I differentiate 1/4 x to the 4, I get 1/4 times 4x cubed, which is just x cubed, which is little f. I'm going to give you a whole bunch of antiderivative rules, and each one of them is just a derivative rule read backwards. The reason these things are important is because when you start trying to connect the area problem to the derivative problem, it turns out the smoothest connection is thinking about not forward derivatives, but antiderivatives. So a fact Antiderivatives are intimately connected to the area problem. The area finding. And I'm certainly not going to prove this to you right now. The specific connection is the fundamental theorem of calculus, which is going to have to wait till like next Wednesday. But I want to give you an example that I think is reasonably convincing. Let's find an expression for the integral, let's say from 0 up to, symbol to use here, let's say 0 up to y of 2x dx. So this is the area bounded by little f of x equals 2x from x equals 0 to x equals y. And I'm using a variable for the upper bound here for the larger, for the b value, because we're going to see that when you think of this thing as a function of y, it becomes pretty neat. Let's see it. I'm just going to label this value here as y. Of course, 0 is over here. Okay, baby. I chose a nice simple function 2x because I know that I can calculate this area exactly without any fancy Riemann sums. It's the area of a triangle. This is the graph. F of x equals 2x. And this area is the area of a triangle. So it's going to be 1/2 the base times the height. You could also do this with Riemann sums, but it's going to be a big pain in the ass, and there's no reason to because it's a triangle. So just use this algebra, or sorry, geometry formula. The base here is y. Right, that length is y. The height here, well, what is that height? It's the y value on the function. It's the output from this function. It's 2x. So this is 1/2 times y times the output here. When you plug in y for x would be 2y. This is the point y comma 2y because we're on the graph f of x equals 2x. The 1/2 and the 2 cancel, and you get y squared. Now, ignoring the difference in variables, how is this related to this? Well, if you take the derivative of this, you get 2x, right? This is like an antiderivative for this, just with the variable swapped. And that's kind of the big idea here that we're going to approach with the fundamental theorem of calculus. That this thing, which we know right now as an area, that's how we defined it, is also an antiderivative for the little function inside. And that was kind of the earth-shattering discovery that like brought Newton to his true fame, and Leibniz as well. It wasn't just that you can take derivatives, derivatives are surely useful, but it was this connection between the tangent line problem and derivatives with the area problem and antiderivatives, and realizing that those two problems are really the same problem, just sort of walking in different directions, if you will. Okay. I do not want to dump too much on you guys this week. Like I said, 5.2 stuff will come next Monday, and then we will get into 5.3, which is the fundamental theorem of calculus. We are already dipping our toes into 5.3. So I'm going to go ahead and let you guys go here for today. Please wrap up that homework set. If you have any questions for me, don't hesitate to ask. And come prepared on Monday for a lot of work with integrals, this new notation we've introduced, and ready to think hard about antiderivatives, which will be a fun little bit of sport for us. But that's it for me. You guys enjoy your weekend, enjoy the weather, be safe. I should have the rest of your grades, so if your exam hasn't been graded yet, just hang in there. The rest of the grades should be in later tonight. That is it from me. Take care, guys.